Welcome to Calc Chats, the video where we chat about calc. This is about the introduction to the derivative. In Algebra 1, we learned about slope, and our idea of slope is very linear. So given 2 points, x1, y1, x2, y2, when we were asked to find the slope, we took the difference in the y's over the difference in the x's, and that was our slope. In calculus, we're going to be doing something very familiar to that. However, I just want to rewrite it as x1, f of x1, and x2, f of x2. So in calculus, we mostly use function notation. So it's the same idea, f of x2 minus f of x1 all over x2 minus x1. Same idea of slope. Looking down here, we've been dealing with slope for linear lines, but now we can look at parabolas, cubic functions, and extend our idea of slope to there. So this is what we call the secant line. We call it the secant line because if you remember in geometry, we would have a circle and a line that would cut through our circle at 2 points. That was called the secant line. So here, our line is cutting through at 2 points. And again, we can use this idea, f of x2 minus f of x1, x2 minus x1 to find the slope of the secant line. Again, here we want to focus on the slope of the secant line, but rather than make x1 and x2, I'm going to call this x and x plus h. So h could be any number. H could be 1/2, it could be 3, it could be negative, well, probably not negative 3, but it could be any number that you wish to be. So again, when we take the slope of the secant line, we're going to take f of x plus h minus x all over x plus h minus x. So this is still the slope of the secant line, but the issue is the secant line doesn't tell us a super accurate depiction, right? We can only really find the average slope. So what we want to use is we want to get h arbitrarily close to 0. So what we want to happen is I want to get really close so that I'm going to be looking at the tangent line. So if I wanted to find the slope right at x, I want to take the limit as h goes to 0 of f of x plus h minus f of x all over x plus h minus x. And if we simplify this, we get the limit as h approaches 0, f of x plus h minus f of x. Our x's cancel out, so we just get this over h. So the idea is that we're making this interval smaller and we're finding the slope at x. Rather than the slope between 2 points, we're finding the slope right at x. So we have a special name for that limit that we just talked about, and it's called the definition of the derivative. So the limit as h approaches 0 of f of x plus h minus f of x over h. So what is the derivative? Looking back on this slide, we can see that instead of a secant line, now we're dealing with a tangent line. And remember in calculus, we had the circle touched at 1 point, that was our tangent line. So our derivative is essentially the slope of our tangent line. Another word you might hear being used for this is the instantaneous rate of change. Because it focuses on 1 point, in this case, this point, focuses on the 1 point and it focuses on the rate of change at that point. So now we're going to be using the definition of the derivative to help us solve problems and find slopes of functions. First thing we need to do is we need to talk about the derivative notation. So when we take the derivative of f of x, we call it f prime of x. We can also notate the derivative as d dx, so the derivative with respect to x of f of x. That's another way of dealing with it. When we're looking at y, we can say y prime, that's the derivative, or dy dx. Those are all solid notations for the derivative. So here we're asked to find the slope of the tangent line at x equals 4 for the function f of x equals 3x squared plus 7. So we're given a point and a function. So in my definition of the derivative, I want to look at specifically x equals 4 for my function. So wherever I see f of x, I'm going to plug in f of 4 because I'm looking at 4. So I'm going to plug in f of 4 here, and right over here I'm going to plug in f of 4 plus h. So just like in this function, wherever we see x in our function, we're going to plug in 4. Wherever we see x in our function, we're going to plug in 4 plus h. So this looks a little bit like this. So the limit as h approaches 0, f of 4 plus h minus f of 4 all over h. That's equal to the limit as h approaches 0 of 3 times 4 plus h squared plus 7 minus 3 times 4 squared plus 7 all over h. So what I want to do is now I want to expand this middle term 4 plus h squared. So that turns into 16 plus 8h plus h squared. And all I did from this step to this step down here was I took 4 squared and got 16. So now when I simplify, all I did was I took 3 and I distributed it to 16, 8h, and h squared to get 48 plus 24h plus 3h plus 7. And then I just multiplied 3 times 16 to get 48. Over here, all I did was I combined my like terms. So I took 48 plus 7 to get 55. And then I just rearranged the order a little bit. So then I noticed that the 55 and negative 55 canceled each other out. So all I'm left with is 3h squared plus 24h. Now, when I'm looking at the limit, the issue becomes h is going towards 0, but I can't divide by 0. So what I want to do is I want to simplify this. So I look at the top and I notice I have an h and another h. So what I'm going to do is I'm going to take an h out of both of them. So I'm going to get 3h plus 24 in parentheses and h on the bottom. Now I see both of them cancel out. So now I'm just looking at the limit as h approaches 0 of 3h plus 24. And now I can just direct substitute 3 times 0 plus 24. And this is going to be 24. So what I found is the slope of the tangent line at x equals 4 for my function f of x equals 3x squared plus 7. In this problem, it's asking me to use the definition of the derivative to find the derivative of the function f of x equals 2x minus 9 across all x values. So again, using that difference quotient, f of x plus h minus f of x all over h. In this case, I'm not given a specific x value, so I'm not going to plug anything in for h. So all I'm going to do is I'm going to take the limit as h approaches 0, and I see f of x plus h. Everywhere I see x in my original function, I'm going to plug in x plus h. So I'm going to take 2 times x plus h minus 9 minus my original function, 2x minus 9, all over h. So now what I need to do is I need to distribute my 2, and I need to distribute this negative. So I get 2x plus 2h minus 9 minus 2x plus 9. And this, I notice my 2x, negative 2x cancel out, negative 9 and 9 cancel out. So all I'm left with is 2h over h. This one's a little bit easier to simplify. All we need to do is cross out the h's. So now I'm looking at the limit as h approaches 0 of 2. There's nothing for me to plug in 0 to, so the limit is 2. So across all the x values of this function, f of x equals 2x minus 9, my derivative is 2. And if I think about this and think about what 2x minus 9 looks like, that is just a straight line. So it makes sense that my slope of the tangent line would be 2. So we talked about just derivatives in general, but we're going to talk about left-hand and right-hand derivatives. Same idea as right-hand and left-hand limits. So I'm looking at f of x equals x squared, and I know it's a U shape. Looking at f of x equals 3x, I know it's a line. So what I want to do is I'm going to consider this piecewise function. So I'm going to consider the piecewise function x squared for x less than or equal to 0, and 3x for x greater than 0. So now I want to look at the right and left-hand derivatives at 0. That's my trouble spot because that's where they're kind of going together. So I want to make sure and see if the derivative is the same. So what I want to do is I want to use my definition of the derivative, the limit as h approaches 0, of f of x plus h minus f of x. So I'm looking at x squared at x equals 0 and 3x at x equals 0. So again, I'm just going to plug in x or 0 where I see x in my original function. So f of x plus h, I'm going to say f of 0 plus h minus f of 0 all over h. Sorry, we need that limit. So I'm taking the limit as h approaches 0, again, plugging this in wherever I see x in my original function. So I'm going to take 0 plus h squared, and then minus f of 0 is just 0 all over 8. So when I FOIL this out, this ends up just being h squared minus 0 is just h squared again, and then h squared over h, I cancel that out to get h. So I'm taking the limit as h approaches 0 of h, which I just get to be 0. So our derivative for x squared at x equals 0 is 0. Now we're going to look at the derivative of 3x. So I'm going to take the limit as h approaches 0, f of 0 plus h minus f of 0 all over h. So when I simplify this and plug this into my function, I'm going to get 3 times 0 plus h minus 0 times 3 and just 0 all over 8. When I distribute my 3, all I'm left with is 3h, and I'm left with 3h over h. Those two cancel, so the limit as h approaches 0 of 3 is just 3. So my right hand and my left hand derivatives do not match up, so I can say the derivative does not exist for y equals x squared, x is less than or equal to 0, 3x, x is greater than 0, at x equals 0. So this is the end of the lecture. Make sure to come to class with any questions you may have. Thank you for watching.